reactions is the first kind of reactions that you encounter during this subject. Okay, and there will be many more, chapter 4, 5, 6, 7, and so on. And next semester also there will be another organic chemistry paper that you will have to take. So basically, introduction. Uh, this first few slide is on the introduction of organic reactions. Okay, basically all the reaction will involve breaking of existing covalent bonds and also forming of new covalent bonds. So in organic compounds, we most of the what you call bond that is between atoms are covalent. If you have an ionic bond, that is normally in inorganic compound. Okay, like for example, sodium chloride or potassium hydroxide, sodium hydroxide. So those are inorganic compound. But in organic compound, contain carbon, hydrogen. Okay, all of the bonds are covalent. So it will involve bond breaking and also bond forming of covalent bonds. So the overall description of how a specific reaction occurs is called the reaction mechanism. So reaction mechanism is like the um, detailed explanation on how the reaction proceeds. Okay, um, how the electrons move from one part of the compound, probably from a carbon or from hydrogen, to another part of reactant, for example. So a mechanism described in detail exactly what takes place at each stage of chemical transformation. And the function is to describe which bonds are being broken first, okay, and in what order. Okay, there's a particular order, and also which bonds are formed, and you can also tell the relative rates, okay, rates of the reactions. So bond breaking, there are two types of bond breaking. One is called heterolytic fission and the other one is homolytic. So for heterolytic fission, you see this first example over here. So for heterolytic fission, both electrons from a bond move together to the more electronegative atom. So that means this X and Y, the line over here is the bond, which is it could be a covalent bond. So inside each bond, normally they are sharing 2 electrons. So in each bond, there will be 2 electrons. So in hydrolytic fission, both of these um, electrons will go to one side of the atom. Which atom? Normally, it will go to the more electronegative atom. So this is based on Pauling scales. Okay, for those who did not take pharmaceutical chemistry 1, especially the BPS student, you have to do your revision on your own because you got your exemption for that paper. So try to see what is the electronegativity trend. Okay, and the result will be two species with different charges. You have the X with negative charge and Y with positive charge. So this negative charge, we will call it as anion, anion, A-N-I-O-N, anion, while the positive charge, we will call it as cation, okay, C-A-T-I-O-N, cation. So heterolytic fission is not really that important for C and CH bonds. Why? Because normally between CH bond, for example like this, C and C, the electronegativity is the same. So how can you give the electron to the more electronegative sides? So that doesn't happen for CC and CH bond. Okay, for CH bond, they have no or little polarization. Then the next type of bond breaking is what you call as homolytic. So homolytics, that means it the electrons split evenly between both atoms. So you see this arrow. Okay, one will go to the X side and the other one will go to the Y side. And before I forgot, okay, for this one, the movement of arrow, the movement of electron, how you draw the arrow is very important. Okay, if you want to show the movement of two electrons like this one for heterolytic, you will use the normal kind of arrow. That means the one that have two, the usual way, the usual way. But for homolytic fission, the arrow is half arrow. Okay, like the one explained here down in the bottom. Okay, full headed arrow indicate movement of two electrons. But for homolytic fission, when there's only one electron move, you use half arrow. So that is important. So in reaction mechanism, how you draw an arrow, be very careful. Okay, so homolytic, they will split evenly to become uh, what you call as free radicals. So X will get one electron, Y will get one electron, but they does not become negatively charged. Okay, this is what we call as a free radicals. And a free radicals is uh, neutral. It is not positive, it is not negative. And they are very reactive species. Okay, and they tend to form bonds readily. So that means it is very highly reactive. Okay, next, reagents. So these are some of the terms that you will encounter throughout the whole the rest of the chapters. Okay, in chapter 5, 6, 7, 8, and probably next for your next paper next time as well. So reagents. So what is reagents? So reactions are started by the addition of reagent rather than using high temperature. So normally in organic reaction, you have to add something to your starting material, for example, so that the reaction can start. And the reagent may be, okay, either a free radical, a charged species, or a polar molecules. So it can be any of these. So how do you obtain a free radicals? How do you obtain a charged species or polar molecules? All can be obtained through the homolytic, sorry, this is typo, homolytic fission or heterolytic fission, depending on the type of reagent that the reaction have. So for heterolytic reaction, form the great majority of organic reaction, which is charged or polar species. It can be classified as either these two, okay, electrophiles and also nucleophiles. So electrophiles, most of the time they are positive ion and also electron loving, but not all the time that it is positive. As you can see over here, you have boron trifluoride, which is also neutral. This is neutral. So electrophiles can be more accurately defined as an electron deficient species. So it lacks electron. So if you draw BF3 in Lewis structure, you will notice that the boron in the middle does not have the octet arrangement. Okay, it still lacks two electrons. So this is considered to be an electrophile. Okay, but most of them are positively charged. Then for nucleophile, okay, they are negative. Most of the time they are negative ions, but it can also be neutral like ammonia, because on this ammonia NH3 there is a lone pair. So macam mana you nak tahu ada lone pair atau tak ada lone pair? You have to know how to draw the Lewis structure, okay, of that particular compound lah. So an electron-rich species that seeks out electron deficient centers and will either have a negative charge or lone pair of electrons available for bonding. Okay, so this one you have group 17 ion, chloride ion, bromide, iodide, and this is cyanide ion, C triple bond N. This is hydroxide ion, OH minus, alkyl, okay, with negative charge. But this one, ammonia, it is not negatively charged, but it contains an lone pair, okay, one lone pair on the nitrogen. Then you have these reaction intermediates, okay, that you have to know. The number one is called carbocation ion. Okay, you will encounter this quite a lot. Okay, sometimes it is also called carbonium ion, but most of the times it will be known as carbocation ion. So when you heard cation, you know that it is positively charged. Okay, and when you add the word carbo, that means carbon that is positively charged. So this is how it looks. Okay, C plus with 3 other bonds to it. Okay, the stability of the what you call carbocation ion is arranged as tertiary will be more stable compared to secondary, and the least stable one is primary carbocation ion. Okay, there is no quaternary. Why there is no quaternary? Because carbon has a maximum of 4 bonds to it. Okay, it can only have 4 bonds. If one of the bond is being converted into positive charge right here, so you can only have a tertiary carbocation ion maximum, which is the most stable, and the least stable is primary carbocation ion. Okay, how do you know primary, secondary, tertiary? So if it's a primary carbocation ion, this carbon over here will be bonded to one other carbon. If it's secondary, it will be bonded to 2 other carbon. If it's tertiary, it will bonded to 3 other carbon. So this will be carbon, carbon, carbon. That carbon can be as simple as a CH3 methyl group, or it can be as complicated as C10 or whatever the structure is. Okay. Then you have carbon ion. So this time the carbon is negatively charged. Okay, the negatively charged, and the stability is reverse compared to carbocation ion. So in carbon ion, primary carbon ion is more stable, followed by secondary, and tertiary will be the least stable. Okay, so this is all of this can be explained by the positive I effect. Ini or this one you have learned in what you call first unit, basic principles of organic chemistry. Then you have carbon-free radicals. Okay, carbon-free radicals can be obtained through homolytic fission. Okay, like this. Then homolytic fission occur. Then you will obtain carbon-free radical, and also this what other species? Okay, for example, this one is Z, so Z free radical. Okay, and the stability is the same like in carbocation ion, which means tertiary free radical is more stable than secondary, followed by primary. So primary is the least stable carbocation ion. Then the last one is carbene. Okay, carbines are neutral species, okay, having a carbon atom, so you still have carbon with only 2 bonds and also 2 electrons to it. Okay, even though it has 2 electrons, it is still not considered as negatively charged. Okay, so this is still neutral. The carbon is still neutral. So that is on the reaction intermediate. Next, we go to the types of organic reaction. So in organic chemistry, there are only 4 types of main reactions. Okay, all of the reaction in organic chemistry can be classified into one of these 4. Okay, you have substitution, then we have elimination, addition, and the last one, rearrangement. So for substitution, okay, as the name goes, you substitute something with something. Okay, for example here, a general substitution reaction. So Z over here, which is originally bonded to this carbon, will be replaced by this new reagent coming in, which is Y. So you have C now, the product will be bonded to Y, and this Z originally that is bonded to the carbon will be removed. Okay, will be removed. So that is how um, substitution occurs. So Z can be hydrogen or a heteroatom. So what is heteroatom? Heteroatom is any other atom besides carbon or besides carbon. For example, you can have nitrogen, oxygen, sulfur, or phosphorus. Okay. These are example no need. Then we have elimination. So in elimination, what the general elimination reaction, normally you will eliminate. Just now in substitution, we substitute, ganti. In eliminate, we will try to eliminate the atom that is bonded to the carbon. So kita nak buang terus. So elimination is a reaction in which removal of atoms or group of atoms from two adjacent carbon. So what does it mean by two adjacent carbon? That means the carbon that is side by side. You cannot have this carbon and then carbon yang kat sini pula. No, it must be side by side if you want to have elimination reaction. So in the substrate molecule to form pi bond. So the reaction involves two sigma bonds being broken. So sigma is single bond. Okay, and for the product, one new pi bond will form, which is the double bond. Okay, so this is actually a reverse reaction for addition reaction, which is the third one. This one example later we'll see in topic number 5. Okay, addition, you add back. So you nak tambah balik. So for example, like this one, you have C double bond C. Okay, you want to add the reagent back to these two carbon. So the pi bond will be broken, one pi bond will be broken, and two sigma bonds will be formed. Okay, hence you will get your product. Oops, sorry. And the last type of reaction is the rearrangement. So in rearrangements, basically, the compound does not lose any atoms. It's just that the atoms are being arranged in a different way. So we can say that these two still have the same molecular formula, but the structures are different. Or in other way, we can call it as structural isomer. This one you have learned in unit number 3, right, in stereochemistry. So rearrangement is a reaction in which atoms or group of atoms are migrated from one side to another within the same molecule. Okay, the product is always the structural isomer of the original compound. So example, you have methyl ethyl ketoxime, which is a structural isomer of N-methylpropionamide. So this is an amide. Okay, we will go straight to the substitution reactions. Okay. Okay, substitution reactions. Okay, under lab conditions, normally these substitution reactions only occur with alkyl halides. So haloalkanes or alkyl halide, which is something that we call as the starting material or the substrates. Okay, substrate, substrates or starting material. So these will be the starting point. Okay, then only you can add your reagents. So in this particular reaction, which is nucleophilic substitution reactions, the reagents that you want to add to this starting material or this substrate is a nucleophile. So hence the name nucleophilic substitution reaction. So alkyl halide will undergo substitution reactions and also elimination and reduction reactions. So it can undergo several types of reaction. So the carbon halogen bond in alkyl halide is polar. So C halogen, halogen is group 17. You can have chlorine, fluorine, iodine, or bromine. Okay, those bonds are polar bond. Okay, halogens have a higher electronegativity than carbon, and the bonds is partially polarized. That means if they have electrons shared between them, the electrons will prefer to go to the halogen side. Okay, so there will be heterolytic fission happening, not homolytic. Okay, because the polarity or the electronegativity is different. So this polarization facilitates nucleophilic attack at the carbon atom by suitable nucleophilic reagent, and nucleophilic substitution reactions occur. So this is how substitution reaction is normally written, as with subscripts capital N. And then you have two types of mechanism, SN1 and also SN2. So they are written like this. Okay. And this example, I'm going to go straight to the, okay, this one. Okay, depending on the structure of alkyl halide, the reaction may proceed via nucleophilic substitution reaction SN1 or SN2. Basically, these two are the same. They are nucleophilic substitution reaction. It's just that they are having different types of mechanism. That means how, it's like if you all want to go to Aeon Nilai, but how you go there is different. One of you could take road yang lalu Cempaka, and the other one will lalu jalan nilai yang besar, or some of you will take car, some of you will take Grab ke. So these are how you go to the product. Okay, how the reaction proceed to the product is different, but basically they are still substitution reactions. So here are example. For example, the first one, hydroxide ions yields alcohol. So this is the what you call alkyl halide or your starting material, and this hydroxy ion OH minus is the nucleophile. Nucleophile will come in and attack this carbon, this C and Br. Okay, bond will be broken and you will get your products. Okay, and you have B and C example as well. So I'm just going to go through. Later we'll see in the slide yang untuk mechanism. Okay, substitution reactions usually perform in polar organic solvents, okay, which can dissolve both the ionic and covalent reagents. So you have to know how to differentiate what is organic solvent. Organic solvent is those solvents that is actually an organic compound. Like, for example, you can use methanol, ethanol, benzene, chloroform. What else? Tetrahydrofuran, dichloromethane. So those are what you call solvents, which are organic solvents. Okay, example of non-organic solvent, water. So water is not organic solvents. So however, the solvent chosen must be a poorer nucleophile, otherwise it will compete with the required nucleophiles. Okay, and another factors that sorry, this is okay, this figure indicates the relative nucleophilicity of methane iodide, okay, CH3I, in different types of relative nucleophilicity towards CH3I in methanol. Okay, this is an example of reaction. Okay, RSI iodide cyanide alkoxide. This is methoxide, bromide, ammonia, chloride, fluoride, and methanol. These are all considered to be the nucleophile. Okay, and this arrow pointing toward this side, denoting that this, for example, RS is the strongest nucleophile, okay, towards the CH3I in methanol. R is alkyl group. This is sulfur. R is any alkyl group. It can be CH3 or it can be CH2, CH3, and so on. So there are four factors that you have to consider to determine which mechanism the reaction will proceed. Okay, the first one is the alkyl stereochemistry, which is the starting material. Okay, the alkyl halide. What is the stereochemistry of the alkyl halide? Whether it is primary, secondary, or tertiary. And then the nucleophile strength. Okay, this is just an example of the nucleophile, but there are many others nucleophile. You can find that. Okay, in textbooks, normally in textbook they will have a list of nucleophile. And then solvent polarity, which is this one. Okay, and the nature of living group. The living group is the halide itself. Okay, there is only 4 living group since your starting material is alkyl halide. The living group will be either Cl, iodine, I, Br, and also F, fluorine. Okay, you have to know which among these 4 is the best living group and which one is the least. I have already put that in the last slide. Okay, we go straight to the mechanism. So SN2 is a bimolecular nucleophilic substitution reaction. The rate of the reaction depends both on the concentration of your substrates, which is the starting material itself, the alkyl halide, and the concentration of nucleophile. So if you increase the concentration of either one of these, then the rate of the reaction will increase. Okay. So the rate determining step involves the participation of both substrates and nucleophile, and this is a one-step mechanism. Okay, dia sekali jalan je. What you see in the middle is a transition state. It doesn't count as step 1, step 2. No, this is what happens in between. We draw it so that you know what happened in between. So this is the diagram of a mechanism. So if you are asked on explain the mechanism of a certain alkyl halide reacting with a certain nucleophile, this is how you have to draw it, especially for SN2. Okay, for SN2, 1, 2, 3 with 2 arrows. The one in the middle is the transition state. So what happened in SN2 reactions? Okay, in SN2, it is a single step mechanism. So a nucleophile, for example, this one, hydroxy, will come in and attack this carbon that is directly bonded to the halide. In this example, the bromine, it can be F, it can be Cl, or it can be I. Okay, so OH, the nucleophile comes in and attack this carbon. Okay, not hydrogen, not this carbon, not this carbon, but the carbon that is having the halide. And you notice the arrow is full arrow. That means both of the electrons from this OH is being used. Dua elektron tu akan pergi bergerak ke C. And what will happen? This OH will share one of the electron with this carbon. Hence, the OH can form a bond. But at the same time, this bromine hasn't fully goes out. Dia belum truly keluar lagi daripada carbon. The bond is not fully bonded. Okay, you see the arrow is also showing 2 bromine. So this is what happened in the transition states. So we call this dotted line as partial bond. Partial. Okay, it's partially bonded to the carbon. This OH is partially bonded to carbon. This bromine is also partially bonded to carbon. And another important thing is that this CH3CH, C6H3, they are in one plane. This can be shown here. Okay, they are in one plane. It's like you are seeing a piece of paper. Okay, nampak satu keping kertas, and you poke it with pencil kat tengah-tengah. So at the end of the pencil is the bromine, and the other end is OH. Okay, but this CH3H and C6H13, they are in one plane. Okay, that means it's planar. Okay, planar. And the product that you obtain. So bromine will completely goes out of this compound. Okay, the bond will be fully broken, and you will get your product. But you see this in red, an inversion of configuration. What does it mean is because of this OH coming in from the back, dari belakang, the back, okay, it change the configuration of the compound. If let's say this is a chiral compound, okay, let's say if this is a chiral compound, if you start with R, then you will end up with S. Okay, it will invert. Dia akan terbalikkan you punya stereochemistry configuration. Okay, if you start with S, then you will have R as the product. Okay, this is what you call as backside attack. Attack dari belakang. The nucleophile pergi dekat carbon ni, we call it SN attack. Serang lah. Okay, it's a term we use in organic chemistry. Okay, so backside attack. And this inversion, there is another name. We can also call it as Walden inversion. W-A-L-D-E-N, Walden inversion. Okay. Then, for SN1, okay, the difference between SN2 and SN1 is the mechanism. Okay, SN1 stands for unimolecular. Unimolecular meaning that the rate of reaction is only affected by the concentration of substrates. Okay, no matter how much you add of your reagent of the nucleophile, you tambah berapa banyak pun, the reaction will still, the rate of reaction will still be the same unless you change the concentration of your alkyl halide, which is the substrates. Okay, but how the reaction occur is it will involve two steps. Okay, first is the formation of carbocation. Then only the nucleophile can come in and attack your carbocation. So first, the halide will go out from the alkyl halide. That means the bond between C and Br will be broken. Okay, so this is heterolytic fission. Br will go out to become Br minus. This carbon will become positively charged. So this is a carbocation. Okay, and the carbocation has a trigonal planar structure. Trigonal planar. Okay, in one plane. Okay, then once you have this carbocation, step 1, okay, step 2 can happen. Now only your nucleophile can come in and attack either from the back or from the front. Okay, sebab now it is free. Dia boleh datang attack daripada depan atau dari belakang. But for SN2, the only free side, okay, the only free side is from the back. It cannot come from the front sebab dekat depan dah ada bromine. It can only come from the back side. Okay, there's only one product it will get, but it will be inverted. Whereas for SN1, since the nucleophile can come in and attack from the back or from the front, you will end up with two different products. Okay, two different products meaning that two different stereoisomers. Okay, you will get S and R. The product is still the same lah. Kalau you dapat ini, for example, it's an alcohol. It's still the same alcohol, but with different stereochemistry. Okay, you can get S or R, and front side and back side attack take place at equal rates. The product is formed as a racemic mixture. Okay, still remember what is racemic mixture? If you have the same concentration of both R and S enantiomer, okay, so it will be a racemic mixture. So that is basically the general mechanism of SN2 and SN1. But I know what you have in mind. How do you know which reaction will proceed via SN2, which one will proceed via SN1? Okay, that you have to refer to these 4 factors that we have mentioned earlier. Okay, the alkyl stereochemistry, the solvent effect, and leaving group effect, and also what is the other one? Uh, Leaving group. Nucleophile strength. Sorry, the nucleophile strength. First, we look at alkyl stereochemistry. So it can be either tertiary, secondary, primary, or methyl. Methyl is CH3X, which is the simple structures. Okay, but normally we'll see either tertiary, secondary, primary. Okay, for SN2 reaction, which is a single step, okay, the nucleophile comes in attack from the backside. It will normally prefer primary substrates. Okay, why primary? Because the compound or the substrate has less steric hindrance. That means it is easier for the nucleophile to come in and attack. Okay, this is methyl. Example, this is primary, this is secondary, and this is tertiary. So if you have nucleophile coming in to attack this carbon, it will be easier for this methyl group, for this primary, than this one and this one. Okay, sebab you nak attack dari belakang. So kat sini, it can attack from this. But for tertiary, very hard. Okay, very hard to undergo SN2. So, tertiary, secondary, primary, methyl. Sorry, this is for SN1. For SN2, methyl, primary, secondary, tertiary. But for SN1, it's the other way around. SN1 prefers tertiary. Why tertiary? Because if this bromine goes out, okay, bond break, it will form a carbocation, correct? But the carbocation will be tertiary. If you still remember tadi, the reaction intermediate, tertiary carbocation is the most stable one. So intermediate structures must, it prefers to be in the most stable form. Okay, so that's why SN1, it needs to be in a carbocation state. So hence, it prefers tertiary alkyl halide compared to primary or methyl. Then based on nucleophile strength, so this one, normally the strong nucleophile will make the reaction to proceed via SN2, while weak nucleophile, like for example water, the reaction will normally proceed via SN1. Okay, example of strong nucleophile is like this alkoxy group. Alkoxy is RO minus. Okay, R can be CH3O. So kalau macam ni, we call it as methoxy group, and hydroxy. So these two can be considered strong nucleophile, but water normally is weak nucleophile. And then you have this negative, SH negative, OH plus. Or in terms of halogen, iodide is having higher nucleophilic strength, okay, compared to bromide, chloride, and fluoride. Okay, this list you can add on your own from textbooks or online references. Okay, then solvent polarity. We have two types of solvent. Okay, polar protic and polar aprotic. Earlier in the slide, I mentioned that all the reactions normally proceeds via polar solvents, but you have two types of polar solvent as well, polar protic and polar aprotic. Okay, polar protic is those solvent that contain OH or NH. Okay, it has the ability to form hydrogen bond. Okay, so what happens is it will stabilize anion nucleophile, decreasing their reactivity by forming a solvated layer around the nucleophile. So it will make, if you use protic solvent, polar protic solvent, it will make your nucleophile strength decrease. So when the strength of the nucleophile decrease, the reaction will normally proceed via SN1, the two-step mechanism. Okay, that one is easier because the nucleophile can come in and attack easily from front or from the back. Okay, but for polar non-protic or polar aprotic solvents, it bind the counter ion of the nucleophile. The counter ion is the positive charge of the nucleophile. Okay, for example, here you have your reagent is sodium cyanide. Okay, the Cn minus is the nucleophile, but you still have this sodium plus. Okay, this sodium plus is the counter ion. This polar aprotic will bind the counter ion and leave the nucleophile free. Dia tak kacau nucleophile ni. So the strength will be maintained. Hence, polar aprotic or polar non-protic, uh, the reaction will mostly goes to SN2. Okay, it will help to facilitate SN2 reaction faster. And leaving group. Okay, the effect of leaving group. Okay, there's only 4 leaving group that you have to know. Since the reaction substrates or the starting material is alkyl halide, is iodide, bromide, chloride, and fluoride. So relative stability of the leaving group, iodide ion has higher stability than bromide, chloride, and fluoride. That means when it become I minus, all of these are group 17. When it receive 1 electron, it will fulfill the octet arrangements. Dia dapat 8 electron on the outer ring. So it becomes stable. So, but among these 4, iodide ion is the most stable. That means if you have iodide attached to a carbon, it prefers to become an ion. It will take the electron between the carbon iodine bond for itself to form an iodide ion, and the carbon will become carbocation. Okay, and this one you can read. Stereochemical consideration, and then this is the comparison. Okay, okay, that is all for unit 4. Okay, sekarang pukul berapa ni? 12:50. I'm just gonna jump into unit 5 first. Okay, if you have any question, you can type later because saya tak cukup masa ni. Okay, in unit 5, dehydrohalogenation of alkyl halide, or the other names is elimination reactions of alkyl halide. So the word dehydro, we want to remove D, meaning you are removing hydro, that is hydrogen, and halogen. So the halogen is the for halogen lah, the carbon, the chlorine, fluorine, bromine, or iodine. Okay, you are removing 1 hydrogen and also 1 halogen. Hence dehydrohalogenation of alkyl halide. So for this reaction also, there are 2 types of mechanism, which is E1 and E2. So as you can guess, probably you already have read a little bit. E2 reaction is biomolecular. It can it proceeds in single step. Sama juga macam SN2, E1 also it's almost the same like SN1, which is a 2-step mechanism. First, you have to form the carbocation ion. So elimination reactions, there are 2 types of elimination reactions. One is called the alpha elimination, or 1,1 elimination, or the beta elimination. So alpha elimination is when you eliminate both atoms or group of atoms from the same carbon. So that's why we use the word 1,1. You are removing from the same carbon. Okay, but beta elimination, 1,2 elimination, when you remove atoms or group of atoms from 2 adjacent carbon. That means side by side, you remove from carbon number 1 and also from carbon number 2. And this elimination of alkyl halide is an example of the beta elimination. Okay, beta elimination. So this is an example of alpha elimination. Okay, CHX3. CHX3 That means you are removing hydrogen and this halogen from the same carbon. So this is an example of alpha elimination. Beta elimination, this one, you are removing one hydrogen from this beta carbon and the other one, which is this L, from this alpha carbon. So that's why it is called a beta elimination or 1,2 elimination. Let's check. Oh, sorry. Slide tak tukar. Sekejap Saya share. Okay, can see the new slide? Saya terlupa nak tukar.
Can, sir.
Okay, alright. So tadi saya tunjuk yang elimination ni, just alpha elimination and beta elimination, just these two slides. Okay. Alright. For the elimination reactions, so alkyl halide will undergo the beta elimination to eliminate HX, okay, hydrogen and also halogen, when it is treated with base to give alkenes. Okay, alkenes. So your product will be alkene. Just now in substitution reaction, the product depends on the type of reagents that you add. If you add hydroxy group, then it will become alcohol. If you add cyanide, then it will become what you call that? Cyanide compound lah. Or if you add alkoxy group, then it will become ether. Okay, it depends. But for elimination reaction, the product will always be alkene. Okay, alkene. So elimination reaction usually require forcing conditions. In other words, it will involve heat and also strong base. So dekat sini you nampak this word strong base. Okay, actually the base itself is also a nucleophile. Okay, how to explain this easier is that all base that is in this elimination reaction are considered nucleophile. Okay, but not all nucleophile are basic. Okay, semua base adalah nucleophile, tapi bukan semua nucleophile adalah base. That means all of these base is considered nucleophile and it can be used also in substitution reaction. But the nucleophile that you use in substitution reaction may not necessarily be a base. So it is not suitable for elimination reactions. Or sometimes the reaction is heated a little bit. Heat kat sini bukanlah sampai beratus-ratus degree Celsius. Normally it is higher than room temperature, or 60 degree Celsius, 70, depending on your solvent that you are using. If you are using methanol as a solvent, or what do you call that, ethanol as a solvent, you probably don't want to heat above the boiling point of ethanol. So you tak boleh nak panaskan lebih daripada 72 degree Celsius. Otherwise the ethanol will evaporate, right? So heat varies depending on the type of solvents each reaction use. Okay, the two mechanism that you have to know is E1 and E2 mechanism. So kita terus pergi E2 lah. So E2 is bimolecular elimination reaction. Okay, the rate is the same like in SN2, determined by the concentration of both substrates and also nucleophile. So if you change the concentration of either one of these, then the rate will change as well. Okay, but for E1, unimolecular, rate is determined by the concentration of substrates. Okay, the reaction involves two steps. Yang E2, one step. Okay, so we look at E2 reaction mechanism first. Okay, over here we have this alkyl halide. Okay, this is a secondary alkyl halide. Okay, the bromine is in the middle carbon, and this is your nucleophile, okay, or base. This is an alkoxide ion. Okay, the product will form an alkene, alcohol, and bromide ion. So these two are byproducts. Okay, what happened and what makes it different than substitution reaction is the site of your nucleophile attack. Okay, in elimination reaction, or particularly this E2 reaction mechanism, you look at this nucleophile, okay, or this base. It comes and attack the hydrogen from the beta carbon. Okay, kalau in substitution reaction, this will comes and attack this carbon or the alpha carbon that is bonded to the bromine. But what makes it different is this thing comes in and attack this hydrogen. Okay, kat sini we have beta and alpha. So what is alpha carbon? Alpha carbon is any carbon that is bonded to a functional groups. You know what is functional groups? If you have halogen, if you have alcohol, if you have amine, if you have carboxylic acid group or carbonyl group. So any carbon that is bonded to a functional group will be known as alpha carbon. All those carbon that is next to the alpha carbon, you call it as beta carbon. So this will be beta carbon. This also will be beta carbon. Okay. And any hydrogen that is bonded to a beta carbon, you will call it as beta hydrogen. Okay. So this ethoxide ion comes in and attack this hydrogen. So basically kat sini ada 3 hydrogen. Okay. But why choose this one? Actually, these 3 are the same. Because this is CH3, the environment is the same. So if you attack this hydrogen, you will still get the same product. So it doesn't matter. Same as well, if you attack at this hydrogen over here. Why? Because this bromine is in the middle carbon. So we call it as this one is symmetrical lah. Okay, if it's unsymmetrical, yang itu kita tengok kemudian later. Okay, so what happened? This ethoxide comes in and attack this hydrogen. So still like SN2, it has a transition state. Okay, transition state. So in this transition, so a transition state, you must draw this bracket kat luar. So when you draw a transition state, you must draw this bracket. If you don't draw this bracket, people don't know that it is a transition state. Okay, you cannot assume people to know that this is a transition state when you draw. You must have this bracket outside. So in this transition state, there are 3 partial bonds, okay, between the ethoxide and the hydrogen. Sorry, 4 partial bond. And then between this hydrogen and this beta carbon, between the beta carbon and alpha carbon, and also between alpha carbon and the bromine. Okay, so these bromines actually haven't fully been eliminated yet. Okay, so partial bond now exists between all that I have mentioned just now. So the last step is now the double bond of the alkene is fully formed, and the alkene has a trigonal planar geometry at each carbon atom. So the other products are molecule of ethanol and bromide ion. Okay, so simple. It's the things that is different than SN2 is the place in which that the nucleophile attacks happens. Okay, in elimination, it will take the proton. Proton to hydrogen lah. Okay, hydrogen is only 1 proton, so we can in organic chemistry sometimes hydrogen is called as proton. Okay, but in SN2, they attack alpha carbon, so that is different. Important feature of E2 mechanism. For an alkyl halide to undergo elimination via the E2 mechanism, the hydrogen and X, hydrogen and the halogen group must be positioned in anti to each other. That means it is pointing different way. Kalau this hydrogen is pointing upwards, okay, this is Sohor's projection. If this hydrogen is pointing upwards, then the halogen must be pointing downwards. Okay, satu ke atas, satu ke bawah. Or if this is located here, then hydrogen must be at this position. Okay, it must be anti and be in the same plane with each other and the carbon atoms in which they are attached. So the elements of HX or must be in anti-periplanar. If it's not in anti-periplanar, then it cannot undergo E2 mechanism. It will proceed via E1, regardless of the reaction condition is suitable for E2. Tapi kalau the position is not anti-periplanar, it will proceed via E1. Then for E1, okay, two-step mechanism. The first step is the same like in SN1, which is the formation of carbocation. Okay, as you can see here, this is a tertiary alkyl halide. So tertiary alkyl halide will prefer to proceed via E1 or SN1 because it get to form the stable tertiary carbocation first. So once the halogen has been removed or eliminated, then only your nucleophile or the base can come in and attack the beta hydrogen. Okay, it can come in and attack the beta hydrogen. So in this case, it can attack this hydrogen or this hydrogen or this hydrogen. These are all in the same environment. Okay, once it takes the hydrogen, then your alkene will be formed. Okay, the product will always be an alkene. This one, I skip. You can read on your own, but this won't be assessed. Okay? 3 slide ni, you all boleh baca, but I won't assess you in test or exam or whatsoever. Okay, other aspects of E1 and E2 reaction mechanism. So the distinction between E1 and E2 mechanism is not as clear as SN1, SN2 because sometimes tertiary secondary alkyl halide will eliminate HX can be from both mechanism. Okay, sometimes both mechanism in real reaction, I'm talking about real reactions, sometimes both mechanism occur in the same reactions. Okay, it's not easily distinguishable like in substitution reactions. Okay, primary alkyl halide will eliminate the hydrogen and halogen only via E2 mechanism only. Okay, E2 mechanism only. Then, okay, this one. Okay, for many alkyl halides, there are two possible elimination products. Okay, this happens when there are more than one type of beta hydrogen available. What I mean by more than one type of beta hydrogen is hydrogen two, they are not in the same environment. For example, like this one, this is via E1 mechanism. Okay, the tertiary alkyl halide below has 3 beta carbons. 2 are identical methyl CH3 groups, and the third is a methylene CH2 group. So where is your alpha carbon? The alpha carbon is the carbon that is bonded to the functional group, which is bromine. This is alpha. All other carbons that is next to it, okay, the neighbors are beta carbon. This is beta carbon, this is beta carbon, this is beta carbon. Okay, and the hydrogen that is bonded to the beta carbon is called beta hydrogen lah. Okay, so these and these are the same. Kenapa saya cakap sama? Why I call it as the same? Because if you want to number the if you want to give the name, you have to start to find the longest chain, right? Of the longest carbon chain. Okay, it can be 1, 2, 3, 4, or you can start 1, 2, 3, 4. This metal will still be at the second position. But for these two hydrogen, they are not in the same environment as these two. So now you have two options. Your nucleophile can come in and attack or take away this hydrogen or this hydrogen. So dia nak ambil mana satu. So let us examine the elimination. Okay, what happen is you will get two different products basically. Okay, you get two different products. Okay, the first one, this what you call OH group or hydroxy group takes this hydrogen from the methylene, okay, the CH2, and the other one, it takes the hydrogen from the CH3, the methyl group, and you will end up with this structure of alkene and these structures. Okay, once you have the product, okay, both of the products, okay, you have to determine which is the more substituted alkene. What does it mean by more substituted alkene? You look at this C double bond C, okay, you tengok kat C double bond C, and check at each carbon, okay, is it bonded to any other carbons? Any other carbon. For example, at this one, okay, this carbon, it is bonded to one carbon, two carbon. Okay, regardless of the length, this can be 10 carbon or 1 carbon, it will still be considered as 1. This is 1, this is 2, and at this position, this is considered to be 1 substituents. Okay, but hydrogen is not counted. So in this structure, this product, okay, the alkene has 3 substituents, 1, 2, 3. So more substituted. But if you take the hydrogen from the methyl group, this is the product or the alkene that you will get. Okay, on this carbon, both of it are hydrogen. And on this side, you have 1 carbon, 2 carbon. So this is 2 substituents. So you have 3 and 2. This is more substituted, less substituted. Okay, the more substituted alkene is what you call as SETZAF. Okay, and this is more stable. More substituted alkene is more stable. Hence, it will be the major product. Okay, while your Hoffman, which is the less substituted alkene, is the less stable and also minor product. You can still get both of them, but you will get this a lot more compared to this one. Probably kalau in percentage, probably this one 80% and this is 20%, for example. This one is the same, it's just different mechanism, E2. Okay, you can still get ZZF Hoffman. ZZF is this one has 1 carbon, 2 carbon, while for these structures only 1. Yang lain hydrogen, hydrogen, hydrogen. So this is less stable. Hoffman. Okay, Hoffman versus ZZF. As you know already from here, the ZZF will be the major product, Hoffman minor. But what if you want to change that? For that particular reaction, you want to have Hoffman punya structure, this one, as the major product. You still want this a lot more than this. You can do that by using a very bulky base, or that means the nucleophile that you use, the base that you are using, is very bulky. Example is potassium third butoxide, which is this one. The structure is this. This is your nucleophile. Or potassium 3-ethyl 3-pentoxide. Okay, this one. So what happens if you use this bulky base? What is the effect? Bulky base increase the proportion of less substituted alkene, which is the Hoffman, formed in elimination reactions. Okay, how? The hydrogen on the less substituted beta carbon are more sterically accessible. That means, okay, yang ini structure dia besar. Okay, it wants to take the hydrogen from these structures. You have beta hydrogen here and beta hydrogen at this position. It is easier for this base to come and extract the hydrogen from this position compared to this one. This is more steric hindrance compared to the terminal hydrogen over here. Okay, so when the base is very bulky, the hydrogen on the less substituted beta carbon are almost exclusively removed. Okay, and the less substituted alkene product predominates. Okay, it's like this. This one is very crowded. This one, it is more accessible. Okay, the what you call the bulky base is easier to attack this hydrogen at this position compared to this one. Okay, hence your Hoffman will be major product, ZF minor. Okay, then this one is regiochemistry and stereochemistry is on the R and S, not so much. This one, the anti-periplana, is just an explanation. You can read this. Okay, for summary, predicting reaction mechanism, which is easier. There are a few slides that I've put to summarize the substitution and elimination reactions. Okay, in which that in certain reactions, all four of the mechanism will compete between each other, and from the what do you call that, alkyl stereochemistry, the nucleophile use, the solvent use, and also the leaving group, we try to see or to predict which mechanism predominates. Okay, but because normally when you have uh, elimination reactions, okay, happening, for example, you have E1 reaction happening, some of the what you call substrates can undergo substitution as well. Okay, but this is, I'm talking about real life, real experiment. Okay, if you do in the lab, not all 100% will go to elimination reaction. Some of it will undergo substitution reactions. Okay, but in theory, we try to predict which mechanism predominates. Okay, this is just some guide. There are a few tables over here that I'm sharing with you, in which you can use to learn how to predict which mechanism the reaction will proceed. Okay, I already provide you with a little bit of tutorial, and what you can do is try to find more questions. Normally in textbooks, they are kind of the last page, they will have questions. Okay, more questions on this. You can try to find other examples of questions. Okay, and try to do it, because you can only, how to say, master this by repetition. Okay, trying to do questions and all of that. And this slide, the last table is quite good as well. So I'm giving you a few choices in which you can try to use to compare which mechanism it will proceed. Okay, so that is for chapter 4 and 5. All right, if you have any questions, you can post it in the Google Classroom. Okay, and I'll try to answer later. Okay, because I have only another 3 minutes. Kalau you ada soalan sekarang, you can ask now. But by 1:20 I have to go. Sorry ya. Stop sharing. Stop recording.